All right, today we're going to dive into something that feels a little bit like magic, but is actually pure, beautiful logic. We're talking about the geometry of logic, basically a way of thinking with pictures to arrive at perfect answers. Let's get into it. So, let me just start with a question for you. How would you draw a perfect shape, say an equilateral triangle, with absolute precision, but without using a ruler with marks on it, or a protractor, or any kind of measurement at all? I mean, it sounds impossible, right?
Well, the answer has this fantastic name, geometrical construction. It's this whole art form of creating perfect shapes, not by measuring, but by thinking. It's a system where logic itself literally forces the shapes to be perfect.
Now, like any good game, there are some very strict rules. You only get two tools. That's it. First, an unmarked ruler or a straight edge, just for drawing straight lines. And second, a compass, for drawing circles and arcs. And the most important rules? No measuring. Ever. No guessing. The accuracy doesn't come from you having a super steady hand. It comes from the undeniable logic of the steps you're about to take.
Okay, so let's actually put these rules into action. We're going to start by building something really fundamental, using nothing but these two simple tools and our own logic.
So, here's our first challenge. Let's build a perfect triangle, and the only thing we know are the lengths of its three sides. In geometry, this is called the side-side-side, or SSS construction. We have no idea what the angles are, just the side lengths.
Okay, so here's how it works. First, we just draw our base, a line we'll call AB. Easy enough. Next, you set your compass to the length of the second side, stick the pointy end on A, and swing an arc. Then, you set the compass to the length of the third side, put the point on B, and swing another arc. And right there, where those two arcs cross. That's it. That's your third point, C. Connect the dots, and bam, you have a perfect triangle.
So why is this guaranteed to be perfect? Well, this is the beautiful part. It's the logic. Think about it. That first arc you drew, that represents every possible point in the universe that is the correct distance from point A. And the second arc, that's every possible point that's the right distance from B. So the only spot that can satisfy both of those rules at the exact same time is where they cross. It's not an estimate. It's a logical certainty.
And this same logical thinking works for all sorts of other constructions. Take the angle bisector, for example. That's a line that cuts an angle into two perfectly equal halves. And yeah, you can construct this with flawless precision without ever measuring the angle to begin with.
And this quote from some Olympiad training material really gets to the heart of it. An angle bisector isn't just a line that splits an angle. A better way to think about it is that it's the collection of every single point that is the exact same distance from both arms of the angle. That little shift in perspective, well, it's a really big deal.
So that idea, a set of points that all follow a specific rule, that's our doorway into the next big concept. We're about to shift our thinking from static, fixed shapes to something a little more dynamic.
You see, so far we've been finding single, fixed points, right? Like the corner of our triangle. But what if a point wasn't fixed? What if it was moving, but it had to follow a strict rule, like you must always stay exactly 5 inches away from this other point? What kind of path would that moving point trace out?
Well, that path has a special name. It's called a locus. A locus is just the path that a point creates as it moves according to some rule or condition. It's basically the answer to the question, where all the possible places this point could be.
Here's a really great way to picture it. Think of a locus like footprints in the sand. The footprints don't just show you one spot where the person stood, they show you the entire path they took, every single point they occupied as they walked. The locus is the complete set of all possible solutions. And it turns out there are a few fundamental loci that are basically the building blocks for solving much tougher problems. So if the rule is stay a fixed distance from a single point, the path you trace is a circle. If the rule is stay an equal distance from two different points, the path is a straight line called the perpendicular bisector. And like we just talked about, if the rule is stay an equal distance from two intersecting lines, the locus is the angle bisector. So now we have two really powerful ideas, constructing fixed shapes with logic and describing the path of a moving point. Now let's see what happens when we put them together, because this is where the real problem-solving magic starts. So here's a key strategy, one they use in high-level math competitions all the time. The solution to a really complex-sounding geometry problem is very often hiding in plain sight. It's usually just the point where two of these simple paths, two simple loci, cross each other.
Okay, let's look at an example to make this real. Imagine a problem asks you to find a point that has to satisfy two conditions at once. Condition 1, It has to be the same distance from point A and point B. Well, we know what that locus is. It's the perpendicular bisector. Condition 2. It also has to be exactly 5 centimeters away from some other point C. We know that locus too. It's just a circle. So where's the solution to the whole problem? It can only be at the 1 or 2 points where that line and that circle intersect. That's it. You've solved it.
And that is the absolute key here. It really just takes these two core ideas, constructions and loci, to crack open problems that seem incredibly difficult at first. You just translate the words of the problem into these geometric paths, and the solution basically reveals itself.
So, stepping back for a second, what have we really been doing here? Yeah, we've been drawing shapes, but more than that, we've been learning to think in a new way, to think like a geometer. And that's a skill that goes way beyond a piece of paper.
You know, when you practice this stuff, you're not just learning geometry. You're training your brain in precision, how to use logic to guarantee a perfect result. You're learning about logical sequencing. You're mastering visualization, seeing solutions in your mind. And maybe most importantly, you're learning a super powerful method for problem solving. Take a big, complex challenge, break it down into smaller, simpler conditions you already know how to handle, and then look for where those solutions overlap. The whole process is about turning words and rules into shapes and systems. It is the geometry of pure logic. So the final question I'll leave you with is this. What kind of real-world problems, maybe in your job or just in your life, could you solve by thinking this way? By thinking in terms of shapes and systems? What solution is just sitting there, waiting for you, at the place where two different paths cross?
Have you ever wondered how you can turn a simple set of words, like stay 5 feet away from that tree, into a perfect, predictable shape? Well, that's exactly what we're diving into today. We're talking about the geometry of motion, this idea called a locus, which is all about the path a point traces when it's following a specific rule.
So let's just get right to it. What exactly is a locus? I know, the word itself sounds a little formal, maybe a little intimidating, but trust me, the idea behind it is something you already get, intuitively. It's actually super simple. Let's just break it down like this. Imagine a tiny point that's been given a command, a rule it has to follow no matter what. Let's say the rule is, you must always be exactly 3 centimeters away from this fixed spot right here. The path that our little point traces as it moves around obeying that command, that path, that is the locus. Okay, so if we're going to put on our official definition hat for a second, a locus is simply the set of all the points that satisfy a given condition. Really, you can just think of it as a translator. It takes a rule written in words and turns it into a picture, into an actual geometric shape. Now, to really get good at this, you need a kind of geometric toolbox, and that's what we're going to build right now. We're going to stock it with the 4 most essential, must-know types of loci. Seriously, once you get these 4 down, you can solve a massive range of problems.
All right, tool number 1 in our toolbox. The rule is simple. Stay a fixed distance away from one single point. So think back to our little walking point. If it has to stay, say, 2 inches away from a central spot, what shape is it going to trace as it moves around? Yep, a perfect circle. And you can see it right here. That fixed point becomes the center, and that fixed distance, that's just the radius. Every single point on the edge of this circle is the exact same distance from the middle. It's such a clean, simple, and really powerful concept.
Okay, on to our second rule. This time, the command is to always be the exact same distance from 2 different points. Let's call them A and B. The path you get from following this rule is something called the perpendicular bisector, which I know is a mouthful. It's just a fancy way of saying it's a straight line that cuts perfectly in half between A and B, and it does it at a 90-degree angle.
And this diagram just shows that perfect symmetry. Go ahead, pick any point you want on that dashed line. If you measure the distance from it to point A and then to point B, those distances are going to be identical every single time. It's a perfect line of balance right down the middle.
So, what if the rule isn't about a point, but a line? The command is, stay a fixed distance away from this straight line. Now this one's a little tricky, because there's a catch. The path you trace isn't just one line, it's actually 2 parallel lines. And here's why. The key thing is, you can be that distance away on either side of the original line. And you have to notice how that distance is always measured at a right angle. It has to be perpendicular. So you end up with one line on one side and another on the other, both running perfectly parallel. And for our fourth and final tool for the toolbox, what if the rule is to stay the same distance from two lines that cross each other? Well, the path that follows that command is the angle bisector. It's a line that slices the angle created by those two lines exactly in half.
And here is what that looks like in action. You actually get two new lines that cut right through the corners where the original lines meet. Any point you pick on either of these new lines is going to be the exact same distance from both of the original lines. Pretty neat, right?
Okay, our toolbox is officially stocked. We have our 4 core locis down, so now let's put them to work. This is where the fun really begins. We're going to learn how to solve a classic locus puzzle. This is what I like to call the golden method. It's a super reliable 5-step plan that works for pretty much any locus problem. First, you hunt down the condition. Second, you translate the words into a geometric idea. Third, you reach into our toolbox and grab the locus that matches. Fourth, if there's more than one rule, you combine the shapes. And finally, you just draw a nice, neat diagram of your solution. Now listen up, because this is probably the most important idea for solving the tougher problems. When a point has to follow 2 rules at the same time, the solution isn't one shape and it isn't the other. It's the exact spot or spots where the 2 shapes cross over, where they intersect. That intersection, that's your answer.
Okay, let's put this to the test. Here's our puzzle. We need to find every possible location for a point, let's call it P, that follows 2 rules at once. Rule 1, it has to be exactly 5 centimeters away from point A. Rule 2, it must be the same distance from point B as it is from point C.
So let's use our method. Let's break it down. Condition 1, 5 centimeters from point A. Come on, we know that one. That's tool number 1 from our toolbox. The path of all the points that follow that rule is, of course, a circle with A as the center and a radius of 5 centimeters. Simple.
All right, now for condition 2. The point has to be equidistant from B and C. And ding, 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 we know that one too, right? That's tool number 2. That's the perpendicular bisector of the line that connects B and C.
And now for the magic. We just combine them. The answer has to be on the circle and it has to be on the line. And where are the only places that's true? Right there. The 2 points where the line and the circle intersect. And boom, those 2 points are our solutions.
So we've nailed the fundamentals, but honestly, we're just scratching the surface. This whole concept goes way deeper. So let's take a quick peek at where this can lead, from some clever math competition problems all the way to one of the most famous curves in all of mathematics.
Check this out. Here's a really cool one you often see in math competitions. The rule is, find every point P where the angle you make by connecting it to points A and B is a perfect 90 degrees. You might think the answer is something complicated, but the locus is, amazingly, just a circle where the line from A to B is the diameter. How elegant is that?
Okay, before we finish up, let's just lock in everything we've learned by talking about a few common mistakes to avoid. First, always remember that the distance to a line is measured at a right angle. Second, don't forget a line has 2 sides, so you'll often end up with 2 parallel lines, not one. And finally, remember that a locus is a set of points. It's usually a whole line or a curve, not just a single spot. So I want to leave you with one last puzzle to think about. We know what happens when a point is equidistant from 2 points. That's a line. And we know what happens when it's equidistant from 2 lines. That's a line too. But what shape do you think you get if the rule is to stay equidistant from one fixed point and one fixed line? The answer is this absolutely beautiful and famous curve, the parabola. And that, my friends, opens up a whole new chapter in the geometry of motion.